This week, we've got Paul Richmond, who is part of the ICCS here in Cambridge, but also part-time 1 day a week at Sheffield. And he's going to be talking to us about sort of work that he's been doing quite long-term on a project called FLAMEGPU. So yeah, whenever you're ready, Paul.
Okay, thank you, Jack. Have you started the recording already?
Yes.
Yeah, okay. Well, in which case, thank you, Jack. Yeah, so my name's Paul Richmond, as Jack said. I'm the team lead in ICCS at Cambridge, and I'm kind of part-time, 1 day a week, still a professor of research software engineering at the University of Sheffield, where I kind of was for a very long time, undergrad through to kind of professor. So yeah, rather too long, I would say. Yeah, but the work that I'm going to talk about today is something that I developed for quite a long time at Sheffield and continue to develop at the moment, in fact. So the talk is titled Lowering the Barrier to Entry for GPU Acceleration in Complex System Simulation. So I'm not really going to explain that title quite yet. I'm going to kind of unravel that a little bit as we go on as to why the barrier kind of needs to be lowered and why, in fact, you might need GPUs for complex system simulation. So the motivation for this talk then is really that of kind of complex systems, and complex systems are systems that exist kind of all around us, whether it be in biology or economics or kind of everywhere. They're effectively just systems where you have got lots of kind of smaller interacting parts that have the ability to produce emergent behavior. So the example that I always use is kind of like a flock of birds, and this isn't a particularly great flock of birds, but it is a video that was CC by, so it's why it's in my talk. Really, I want you to imagine that you're looking at a murmuration of starlings, and you've got this beautiful behavior kind of flowing and moving around in that kind of nice mesmerizing way. And as I said, these kind of complex systems, they exist at different levels of biology. They exist kind of all around us. And it's little surprise that, you know, with simulation being the third pillar of science, that we would want to use computation in order to study them. So one way in which you can do that is through a technique called agent-based modeling, sometimes called individual level modeling. An agent-based modeling and simulation are an approach which allows you to kind of study and explore a complex system. In its most simplistic form, this approach really just needs a model in which you define the behavior at an individual level. So you express the behavior of the individuals within the system, but you don't describe the system level behavior. You provide inputs to the model. So whether that be the kind of the initial conditions of the individuals, perhaps the environment, perhaps some environmental constraints, and then you simulate all of those individuals. Importantly, you simulate the interactions between them, and what happens is it produces kind of nice, beautiful, emergent behavior. So if you consider the kind of the flock of birds example, then there's a famous model called the Boyd's model, which is a model for looking at groups, behavioral groups, so flocks, schools, herds, and it suggests that what you can do is you can define that kind of beautiful emergent behavior by specifying individual behaviors that express three different rules. So cohesion, which is effectively stay close to the group. You imagine birds would do that to kind of maintain kind of safety, stop themselves being eaten from predators, perhaps. Avoid collisions, that's fairly obvious. You don't want to collide with your kind of neighbors whilst you're kind of flying around in the group. And then alignment, which is matching the speed of your neighbors. And by expressing just those three simple rules, you can produce computational simulations that produce those same beautiful effects that you'd see within a murmuration of starlings. So agent-based modeling is also, it's a really nice method if what you can observe, so the system that you observe can be kind of observed at the individual level. So if you're thinking about modeling people, or you're modeling, say, biological cells, and you have lots of data available at that level, it's kind of quite a natural method to kind of express and describe that behavior. So to do the modeling is quite natural, providing that you can then simulate them and observe and see what happens as an emergent system. So it's little surprise then that the agent-based simulation presents somewhat of a computational challenge. The first kind of computational challenge is that, you know, simulating individuals is expensive. If you were to try and study a system by expressing, say, sets of differential equations, it'd be much cheaper than having to simulate all of the individuals within them, produce emergent behavior, and so on. So there's a computational challenge just in terms of simulating systems, simulating individuals, particularly when you want to scale that up. You know, if your complex system is something like a brain with kind of many millions or billions of cells, then it's extremely expensive to kind of perform computation in that way. So it's little surprise that you'd then maybe think, well, parallelism is a natural solution to that, and of course it potentially is. But it's unfortunately not that simple. So parallelism obviously now is kind of everywhere, whether it be multi-core CPUs, whether it be data parallel GPUs, or any kind of thing in between. There's kind of lots of parallelism available, but the problem with applying it to an agent-based simulation is that doing so for kind of like a general case is really difficult. Yeah, so there's no parallel or no unified parallel model for an agent. And because of that, it means the translation of your model into code, into the implementation, is fraught with difficulties with things like race conditions and various other problems that you'd have in implementing it within a parallel kind of environment. So agents are heterogeneous as well. So this is problematic for things like data parallel architectures, where if you've got agents expressing lots of different behaviors, then it means that it kind of fundamentally breaks the data parallel model of things doing the same thing but being applied to different data. Agents do communicate. They communicate, and that's very, very important to the interaction. If agents didn't communicate, they'd effectively be embarrassingly parallel, and it would be much more simple to kind of simulate them. But because they communicate, you have to worry about how that is handled within a parallel environment. Agents don't stay still. So again, kind of because they don't stay still and they communicate, any data structures that you build to kind of improve the performance of that communication, whether it be in space or across a network, is dynamic. So you need to continually rebuild data structures, which is costly, expensive, and requires kind of understanding of parallel programming. And perhaps the most important one is that the landscape of parallel architectures, both in terms of the architectures and the programming models for developing on them, is complex and confusing. So particularly to an agent-based modeler, someone who's maybe studying cellular systems, they're not necessarily computer scientists or software engineers. The prospect of trying to utilize parallelism, the prospect of trying to utilize things like GPUs is quite daunting. And you know what they really want to do is write models, not write highly efficient GPU code that requires probably lots and lots of training to be able to do that effectively. So this is where FLAMEGPU comes in. This is where the importance of lowering the barrier of entry comes in, and Flame really has the ambition of lowering the barrier of entry by creating an abstraction that uses the GPU but abstracts it and hides it away from users. So not only kind of abstract GPUs away, but abstract kind of parallelism completely, so that a modeler can express and write a model, and really that whole process of how it then gets implemented in parallel, how it gets translated into GPU code is completely hidden, and they can just reap the benefits of potentially high performance. So FLAMEGPU was originally developed then as part of my PhD. So in its very early form, it looked quite different. When I initially started my PhD, there was no kind of GPU programming models available. I kind of initially started to explore the idea of agent-based simulations on GPUs by considering kind of what was called GPU, so the use of kind of shaders and graphics primitives and misusing the graphics pipeline in order to kind of do general purpose compute. Things have moved on quite a long way, fortunately, since then, but this is kind of where the origins come from. It's had a second major release last year, and that really has been a massive undertaking in the development. And we've spent a team of roughly 4 contributors have spent quite a number of years in redeveloping that piece of code. That's been supported by my kind of previous EPSRC Research Software Engineering Fellowship, as well as a number of other research projects that have both contributed and used FLAMEGPU quite extensively. It's a big and complex code base, so I don't even know how many lines of code it is, but there's a huge amount of development effort that's gone into it. It supports some really significant research projects. So I mentioned some EU projects. Mostly they're around computational biology. The industrial work tends not to be biology based. It tends to be focused on kind of infrastructure simulation. So simulating people, simulating vehicles, simulating particularly the rail environment. We've got an ongoing project at the moment with Fujitsu where we're looking at transportation modeling, so large scale simulation of vehicles on road networks. And it's got a growing and active user base. So I know that since our last release at the end of the year, we've had over 100,000 flame simulations. We have some kind of opt-in telemetry that runs in the software. So we do collect some usage statistics, which is really, really nice, particularly important for a research project because it means that we can make cases for further funding and things like that. And it's also supported by the NVIDIA Research Accelerator program. So this provides some access to NVIDIA development technicians, which has been hugely important in kind of some of the optimization that we've done and understanding some kind of really detailed features of particularly the NVIDIA hardware that it's been implemented in or on. So key to the idea of FLAMEGPU then is the modeling itself, so the representation of an agent. So FLAMEGPU uses what's called state-based representation. So state-based representation means that we effectively use a state machine to represent agents. The particular brand of state machine we use is something called a communicating stream X machine. If you're familiar with just a standard state machine, then it is effectively a state machine that also has the ability to send and receive information and probably some other features that I've forgotten. But it's effectively a state machine with communication. And that communication is kind of really important because it allows us to define functions that transition the internal state of an agent by considering kind of external information. So I'll give an example of this in just a moment, but in terms of the state-based representation, it means that we can have heterogeneous groups of agents. So we can represent agents in different time points by using kind of states. So if you think about something like the cellular model that I mentioned earlier, cells may be in different states or different biological states. They may be dividing or migrating or doing any number of biological things that cells do. And it means that by using states, we can group agents in homogeneous groups, but have heterogeneous behavior across a whole population. It's really important when it comes to translation onto GPUs later. There's a separate model of the structure from the behavior then. So we can describe the actual, the model, we can describe the kind of the way in which states interact and the different functions, the different types of communication, and we can separate that from the actual functions themselves. And again, that's kind of slightly easier to kind of understand with an example, which I'll give you in a moment. Importantly, there is this idea of indirect communication via messages. And indirect communication is important because it means that we can remove a lot of the problems that you might have with race conditions if agents were to kind of interact directly. It means that by communicating via messages, we can make certain assumptions about the way in which, or the time in which information is communicated, and it provides us an opportunity to kind of create synchronization primitives. So the simplest example of a model that you could have using state-based representation is kind of like a two-state model where your agents exist in the initial state. The first function that they perform would be something like a function called send locations. This simply takes the internal state of the agent. The internal state is just a collection of variables and outputs them to a message. Yeah, so it might, for example, send out a message with its location so that other agents can potentially consider that location in the future. The second function then is dependent on that particular location message, and it would, for example, read all of those messages or a subset of those messages, consider them in how it responds to the other agents. So it might consider the positions of all of the other agents and then apply some repulsive or attractive force and then update its internal position. So update its X and Y position by creating some kind of creating an attractive or repulsive force. And that's what you saw in that initial example that's on the screen, if it'll run again. No, it seems to not want to run again, but oh no, there we go. So this is the simplest model that you could possibly have. It's called the circles model, and that's exactly what that does. Agents communicate their positions, an attractive and repulsive force over a fixed spatial distance. And what happens is that converges into these kind of nice spherical shapes where it's kind of balancing those two forces. And they form these kind of, well, it's called circles because it was originally 2D, but in 3D, they form these nice spheres. And over time, it kind of stabilizes, and some of those spheres kind of combine if they end up kind of close enough. So that's a very simple model, but you can consider obviously much more complicated models. And this is a model of, I think, I can't remember what it is. It's that old now as an image, but I think it's a model of the European economy. But as you can see, it's got states, it's got functions, it's got behavioral dependencies, but it's rather a large and complicated model. And this is why this kind of fundamental state-based representation is absolutely important, because we can separate the model description from the implementation, and it avoids us having to kind of capture all of the dynamics of those interactions within the actual implementation. We just simply describe it as a model and let the framework like FLAMEGPU do the translation of that to kind of to the parallel environment. So to give a kind of a bit of an example then, what I don't want to do is present like an entire tutorial into Flame. There are tutorials online that you can look at and see all of the code. So there's a little bit of code that I'll show you, but it's really just to give you a flavor of how things are working. We have an API, it's C++. So you can create, for example, an agent description object. So this is a description of your agent. You can add variables to it. So these are effectively represent the internal state of the agent. So things like X, Y, Z, like its position. In this case, this is the circle model, and it has an additional variable called drift. And part of the behavior, we will kind of update the drift over time to see how far it's moved. And then we can have an approximation then for measuring whether or not we've converged by considering the drift across the whole population. And we can add new messages. So we add messages and we add, so we add functions and we can add messages. So the functions can depend on a particular message. So in this case, we have an output message and the move message. So it represents the graph that we saw on the previous slide. There are two functions defined, the output message function and the move function. And we can see that we set a message dependency on each of those. One of them is set as an output and one of them is set as an input. So what is left to do is kind of now describe the actual function itself. So this is the move function for that particular model. So it has this kind of strange function definition format. We have like a preprocessor that hides actually quite a lot of complexity around kind of template programming that goes on behind the scenes. The three arguments that you have are kind of the name of the function, and then there is a prototype that describes the message input and the message output. So for the move function, we know there is a message input because we want to consider all of those location messages. And there is some specialization that goes on here. So we are saying for this particular function that we are going to use brute force messaging. So I'll talk a little bit about that in a moment, but brute force messaging effectively means consider every single message within that message list. And because this particular function doesn't output a message, we have message none for the output message parameter. So you can see then the kind of the script that defines the behavior is relatively straightforward. If you know any C++, or even if you know kind of Python, it doesn't kind of look that kind of horrendous. We have this singleton that we can use to get information for each individual instance of an agent. This behavior will apply to every single individual, but we can get the individual state conditions of the agent. So we can get the X, Y, Z. We can do some computation. What we have is this nice message iterator that says kind of loop over all of the messages that are available to us. And again, do some computation. So this is just calculating distance, perhaps applying this repulsion factor. And then finally, when we've considered all of the messages, we will update the internal state by setting the agent's variable X, Y, and Z get updated. by applying some force function. So in terms of the script, it looks relatively straightforward. There's certainly nothing that kind of looks like GPU code in there. In reality, this code actually runs within a GPU kernel, but there's nothing to kind of indicate that that is the case. You're not having to deal with threads or blocks or groups or anything that you typically would within a GPU program. So the kind of the complete process then, although I've only shown you like a little snapshot of things that you might do with the Flame API, there's lots of things that kind of exist also within there. There's the ability to specify agents, so vectors of agents for initial conditions. There is visualization. There is a whole bunch of other things that you can do, things like the environment, the message definitions, and everything else. So what you would do to describe your model is you use the API, you write your model description, you write your agent functions, and the FLAMEGPU API will then translate that through to optimized CUDA code on an NVIDIA GPU and allow you to perform a simulation. So if you are so inclined, you can specify visualization configuration, which means that you can either run the simulation just kind of non-graphically and output some logging. That logging can be at the individual level, or it can take aggregate data across populations. Perhaps you want to plot how a particular variable of an agent changes over time with respect to the group, or you can produce these kind of nice interactive visualizations. The visualizations have the benefit that you can actually, well, because they're interactive, you can modify the behavior as time progresses. So you can say change environment variables that control the agent's behaviors, perhaps the weight of particular forces that are applied. So we had the flocking example, and I'll show you how that can be kind of manipulated over time kind of slightly later. And what we've also done for FLAMEGPU 2 is we have provided Python bindings. So this is really important because a lot of modelers, although C++ is a nice interface, lots and lots of people use Python for everything. And Python's a really nice way to express a model, presents quite a few challenges in terms of how we actually go about doing that. And I'm going to talk about those in a little bit more detail, but we effectively are using Swig to wrap our API and provide Python bindings with some other cleverness that I'll talk about later. So we could have used PyBind for this, but we chose to use Swig. I slightly regret it. The reason behind that was because we intended to perhaps have bindings to other languages, and Swig would permit that. So things like R. We've never got round to that, but I guess it does present us with the option to potentially do that in the future, which is quite nice. So I'm going to talk a little bit about some of the challenges then that we face in the kind of the glue part, so the library, so how we do that translation. And I've kind of broken this down into a number of challenges to kind of keep those slightly separate. So the first is the idea of reducing data movement. And if anyone's done any GPU programming or optimization, effectively writing code for a GPU is just a challenge of trying to minimize data movement through the different hierarchies of the architecture. Yeah, so when it comes to writing GPU code and when it comes to translating models into the GPU for Flame, what we want to do is really minimize the amount of memory movement that takes place. And the way that we do that is through the message specialization. This is a really important part of it. For most models, the most significant factor is the message iteration, because you're considering so much more information than you would with functions that output messages. So it makes sense that that's the place that you kind of optimize and improve. So the specialization means that you can consider only a subset of messages. And that means that you're minimizing the amount of data that's moved. We also employ some kind of clever techniques to make sure that we use the GPU cache hierarchy very efficiently, so that we're not only reducing the number of total messages, but we're keeping messages that are important to kind of groups of agents within a cache hierarchy to get good hit rates, so that we get efficient reading of those messages. And we use different spatial data structures behind the scenes in order to do that, which are kind of constructed dynamically every simulation step. So message brute force is fairly straightforward. Consider everything. We have spatial messaging in 2D or 3D. So this is where you consider only a subset of the messages based off your spatial location. So for things like the bird model and the circles model, that's quite important because you only care about a certain spatial neighborhood. We have 1D, 2D, 3D array type messages. So this is really to support an older generation of agent-based model that exists in this kind of chessboard-like environment. And then we have bucket messaging, which is really a primitive that allows us to do things like network messaging, where you have many agents within a particular location. So this allows you to consider models where you might have lots of agents at a particular location. So if you're doing epidemiology, it might be considering all agents within all people within a building or within work or within a particular social group. So the second challenge then is GPUs keep getting bigger. And, you know, this is not necessarily a bad thing, but it does present somewhat of a challenge when it comes to the GPU side of things. So when I first started Flame back in kind of 2011, you know, the level of parallelism has grown, depending on what metric you want to use, by kind of 33 times. So that's quite substantial. You know, I will admit that CUDA cores are not a true reflection of the level of parallelism, but they're a reasonable proxy for it. So that's why I've used them. But it means that people have to write really, really big models in order to fully utilize a GPU device. So the model that they wrote kind of, you know, 10 years ago is, you know, it has to increase by a factor of 33 to utilize a device to its full extent. That doesn't necessarily always happen. You know, people, particularly agent-based modeling, if they've never used FLAMEGPU before, they're probably coming from an environment where they've written models on software that targets kind of serial execution on a CPU. So they might only have quite small models, perhaps only a few thousand agents. It's not going to be anywhere near to keep a GPU busy. So one of the things we've done to kind of counter that is provide the ability to simulate ensembles. So given a particular simulation, given a particular model, so in this case, this is just the simple circles model that I've used for it to be illustrative. It means that what we can do with an ensemble is simulate multiple configurations of that same model. So that could be different input states, it could be different environmental conditions, but what we do is we effectively allow those to overlap and mean that we can utilize the GPU resources over time much more effectively and kind of bunch them up together. And this is really important for multi-agent simulation because they usually are stochastic. So doing a single simulation is usually not enough. You normally need to do a bunch of simulations and then take some statistical observation of the emergent properties. So ensembles is really powerful way to utilize the GPU's kind of increasing levels of parallelism. So related to that then is challenge 3, which is heterogeneity. So as I mentioned, you know, a complex model means that you've got lots of potentially different states, potentially got different agents within a system. And the more complex your model becomes, although Flame has this nice ability to group agents because of the state-based representation, although it can do that, it means that your groups become quite small. You suffer from the same problem because if you have small groups and your agent functions are being applied to small numbers of agents, you're not getting good utilization out of the device. Which is problematic. So you end up with a very long serial timeline of execution of all of these different agent functions, and they end up underutilizing the device for all of them. So the way in which we resolve that then is by using dependency analysis. So because we can construct these nice kind of directed acyclic graphs of behavior, what we can do is we can look at the dependencies between different agents, between different states, between different functions, and work out where functions can concurrently execute. So if we have 3 different agents that all output different messages, we know that they can all occur within the same layer and we can schedule those to execute at the same time. So we use a feature within CUDA called streams, which allow us to do that. And it means that we can, you know, even though we have divergence across the model, we group them in similar states. And even though we have heterogeneity within the model, it means that we can still get good utilization out of the GPU device. There are obviously some kind of little gaps that will get filled or that need to kind of get that will exist because of different execution times, but it does allow at least some overlap of execution and to get some good performance out of the GPU. So The next challenge is conflict resolution, and this is one that we've kind of scratched my head around for a number of years, because it's resolvable within Flame, but I don't like the way that it's resolvable. So what we've done is something which I think is quite nice. So first of all, to explain why conflict resolution occurs. So if you consider like an older kind of 2D chessboard type agent-based model, in this case, on the left-hand side, we've got the current state where we've got two red agents existing within the board. Now, older agent-based modeling software, serial software, would randomize the order of agent movement, and an agent would move, and then the next agent would move, and there would never be any conflict. Whereas in parallel, that's not the case. So we have this kind of slightly darker gray grid, which represents perhaps some attractive environmental property of that grid cell that means that both agents would like to move there. Now in the Flame implementation, what would happen is both things would try and move at once to the same place. That may not be a problem, but if you're wanting to reproduce the same model that the serial implementation had, then it becomes a problem, because we have effectively a race condition there. And Flame has a solution for that. Which is on the right hand side, and that solution is that you use a process of kind of iterative bidding. So if you start in the top left, we have this same situation. We have two agents requesting to move to the same cell, and the solution that we have is we let the cell decide who would like to, or who it should allow to occupy that position. So in this case, it can be based off priority. That might be randomly assigned to the agents, or it might be based on some internal property of the agent. If it's randomly assigned, then actually you can reproduce the same serial behavior as if the random order had been selected in the serial implementations. But this cell will say, well, I choose you to move, and this agent will now be allowed to move, which leaves the kind of state after this iteration that one of the agents is resolved, but one of them isn't, because it wanted to move and couldn't. So we have to repeat the process, and this cell will pick a new location and it will move. So it's what's happening here is we are introducing some serialization, and in the worst case, and the worst case would be it would have to be a very dense model, but you could potentially have 9 sets of conflict that would have to be resolved. In Flame, that's fine. You could write 9 stages of this kind of iterative process. But this is rather breaking the principle that we had at the beginning, which was to hide the fact that we have parallelism. So although you can do this, it fundamentally breaks that idea of kind of lowering the barrier to entry, because you're having to write a different model to the person who's written a model for their serial simulator that's never had to kind of worry or consider this. So the solution then is to kind of abstract and hide this conflict resolution inside what we call a submodel. So the submodel has an entry and an exit point, and what it will do is it will iteratively apply this kind of this conflict resolution process, has an exit condition that will allow it to exit early. So if every agent within the system is resolved, it will exit early. Normally for this type of movement, it takes 2 or 3 steps rather than the full 9. But because we can abstract that now into a submodel, we can reuse that conflict resolution model within any other model. So it's what we're doing is yes, we have to express it in that way initially, but this kind of model can be reused, and we can express different models for different types of conflict resolution. So it could be, in something like a chemistry model, there might be a kind of a conflict resolution in bonding, where you've got different chemicals that want to bond together, or cells that want to interact together, and you can write kind of a submodel to represent those different conflict resolution processes, and then reuse them and abstract them and provide them to the users. So it means that we can do nice things. So this is a famous example of an agent-based model called Sugarscape. So this is a bit like a societal model, if you like. People or the agents, not people as such, but the agents migrate to these areas, these hotspots of where sugar is occupied, and they will kind of slowly migrate across the model based on the density of sugar that is available. So it's really a model for understanding economics. So the fifth and last challenge that I'm going to talk about then is high-level language support. as I said, we wanted to support Python. That was something that was a priority from a very early stage of rewriting Flame. Now, if it was just a case of mapping an API to Python, it wouldn't be too problematic. The challenge that we have is that we have to also translate the agent behavior into Python. So this requires some magic because that behavior needs to be compiled. It has to execute on the device at the end of the day. And that requires two things to happen. So first of all, we have to compile dynamically. We have to compile at runtime, use just-in-time compilation, and we need to get it from Python into something that can be compiled. The way in which we've done that then is we use a library called Jitify for doing runtime compilation of the C++, and to translate Python through to C++, what we do is we actually have a transpiler. So if you have a look at the left, you can see the Python implementation of an agent function, the C++. The way in which you actually write the code looks very, very similar. So what we do is we create, through the transpiler, we will step through the Python abstract syntax tree and translate it directly through to C++ code. I expected this to be broken very, very early, actually. And it hasn't been yet, and people have done all kinds of wonderful things with this, and it seems to have stood up to quite a bit of usage. Now, obviously, we can't translate everything. There are things that you can do in Python that don't translate quite as nicely into C++. We don't support things like dictionaries, but what will happen is if you try and translate a Python, if you try and kind of transpile, it will give you a translation error and say, yeah, that's not a feature that we support at the moment, go away and do something a bit different. But if you're just using your Python for scripting the behavior, then it can be translated quite effectively. And we have a collab on the main FLAMEGPU website. You can click a button and you can try that out and have a little go with it. And everything happens within the browser, but everything behind the scenes is being run just in time compiled. I think what I'm going to do actually is I'm going to skip over some detail here because there are some technical things that I could talk about to do with how we do that kind of just-in-time compilation. But I think what I'd like to do is get on and show you some kind of results of the model, or the results of Flame. So this is a visualization of a flocking model. So I've used that quite kind of early on. And this is, I can't remember, maybe 100,000 agents or something like that being simulated individually. I think it zooms in a moment so you can see what's happening, but they've all started in a random initial configuration, and now they're interacting with those three rules that I described at the beginning, cohesion, alignment, and the other one. And they're kind of interacting together, moving around, flying around, forming these nice murmurations. And because this is an interactive simulation, it's running at least 60 frames per second. We can kind of change some of the global parameters. So things like the separation radius, the steer scale, or even the time scaler in which we kind of integrate over. And it means that we can change the global emergent properties by kind of varying those rules in real time, which is quite nice for experimentation. It's really nice to be able to have the visualization because it's such a visual model. Of course, with the GPU, the visualization effectively comes free. As all of our simulation is already on the device, we can translate it through to graphics primitives and render it without very much cost at all. So we've done a bunch of other kind of probably less visually impressive, but from a modeling perspective, far more important things. So there is modeling of neuroblastoma, EU project called Primage. It kind of looks not very interesting to look at as a visualization, but it is in fact modeling kind of tumor growth. And we have done this by doing kind of like a hierarchical approach to the modeling. We've gone up to kind of like 1 billion cells using kind of patches of simulation, all separately run within FLAMEGPU. Lots of pedestrian simulations, movement of people around different environments. So this is the Olympic Village way back. And then vehicle simulations. So this is a really simple road network with vehicles zipping around. We're doing far more complicated vehicle networks and interactions at the moment. And then looking at things like highly complicated interaction models between people. So looking at enforcing kind of, so this was a model for COVID simulation, looking at kind of entry and exit onto rail carriages, and trying to enforce the kind of the 2 meter rule within the platforms and how that impact the kind of the flow of people. So to look at performance then, so one of the things we can do is we can look at kind of benchmarking. So we have used the circles benchmark quite extensively to look at how the model scales. So the graph on the left is showing kind of a brute force implementation and a spatial messaging implementation of that model. So what you can't see on the left hand side is the spatial model at all, because it just looks like a flat line along the bottom of the axis. If you zoom in, you can really see the extent in which the spatial messaging, so the message specialization, is able to improve the performance. It's phenomenal difference. So message specialization remains an area of kind of active research in which you know, we constantly implementing new ways to kind of specialize messages and improve message performance. The question I always get is how many agents can you do? Of course, there isn't a straightforward answer to that, because it depends entirely on the model, how much internal state the agent has, and it depends on what communication on what message specialism is being used. So it is highly dependent, but what we can do is for a particular model, we can look at memory usage and project that. So we've never gone quite this big, but you could do, say, 500,000 or 500 million agents on a H100 or an A100 with 80 gigabytes. That's rather large number. We have had someone just this week request on our discussion forum the ability to simulate multiple billions of agents, which requires a bit of a rethink, because we're going to have to start paging things in and out of memory. I'll go to a multi-GPU approach. The other thing we can do is we can implement the same models in Flame across a range of existing agent-based modeling frameworks. So I kind of like this result, because I can just casually throw in the fact that we've got 100,000 times speed up over one of the competing simulators. Now, these kinds of numbers it's really an apples and oranges comparison, right? Because these other simulation frameworks are not doing this. Well, they're doing the same model, but they're not doing it the same way. They're not necessarily optimized. They're not parallel, but they are what is available if you're an agent-based modeler and you want to write a model. These are the platforms that you would typically use. So we see that Flame is, you know, at least 1,000 times faster than the next best simulator. So that's agents.jl. That's a Julia implementation for the Boyd's model. It's 100,000 times faster than the worst, which is Mesa. The simulation, so the numbers there represent hours, minutes, seconds of the simulation. Simulation time for Flame, for reference, was 51 milliseconds. This is excluding compilation time and things like that, but the other simulators also exclude that. Agents.jl does just-in-time compilation, just like we do. The other model that we've implemented here is called the Schelling model of social segregation. Again, another famous agent-based model. And yeah, so Flame takes roughly 70 milliseconds. So we're about 18 times faster than the next fastest simulator. So this is one that has got a lot of conflict resolution. So the serial implementations don't have to do the iterative things that we do. We have got a submodel in this that deals with it, which is why we're not quite as good as, say, the Boyd's model, which doesn't have conflict. So before I finish, it would be a shame not to kind of mention all the nice research software development practice that's gone into Flame. And given that I've been kind of building a group and training RSEs for some time, and the Flame software is my kind of baby, I've really kind of tried to push the boundaries of how much of this we can kind of get within the software. So we've done a lot of things that I would consider kind of good practice, and so should everyone. But you know, we've used things like CMake and unit testing, continuous integration, semi-automated continuous delivery. So we have kind of triggered release actions, documentation and user guide, linting, community support. Importantly, we've just published a paper on FLAMEGPU, and what we've done within the kind of data availability statement is we've made a statement about how the software goes about implementing the FAIR for research software principles, which again kind of highlights how important they are, and shows kind of what actions we've taken in order to kind of make sure that the software and the results and all of the graphs and everything within there are completely reproducible. So I'll conclude then and say FLAMEGPU 2 builds upon like a decade of experience in agent-based simulation on GPUs. I have been, so Flame is just one of the GPU type things that I have done in the past, but it's the one that has kind of been around for quite some time, one that I've kind of stuck with. It's a good piece of software because it provides flexibility without losing performance. So it's not an implementation of, say, a cellular modeling framework or a pedestrian simulation framework, but it has the ability to simulate all of those things. It's very, very general in what it can simulate, but it doesn't sacrifice performance in order to do so. So it can compete with kind of specialist implementations of even a particular instance of a model written purely in GPU code. Exposes very high levels of parallelism by utilizing ensembles and taking advantage of concurrency. It abstracts parallelism of the GPU away, so it kind of really does lower that barrier to entry for use. You can run it on in a notebook and take advantage of GPU backends. And it has this nice flexible interface with Python bindings. So it's all nice and free. It's under an MIT license. Feel free to have a play with it or get in touch if there is some functionality in there that is not there that you would like to be there. And that's me. Thank you.
Cool. Thank you, Paul. Does anyone have any questions? Lots of people behind here.
Hello.
Oh, you want to go Stephanie down to Arian?
Oh, that's fine. So currently your code is written in CUDA.
That's right, yeah.
Have you worked anything towards portability?
Yes, it's a great question. So the reason that we've done it with CUDA is because historically it has provided flexibility beyond what you get from some of the kind of the more portable approaches. So things like the just-in-time compilation at the time of us implementing it were not available in any other approach. So that is not true with HIP and HIP-SYCL now. There is equivalent functionality. The way in which the software is designed is modular in that we could write different backends for it. And that is something which I would very much like to do. It's something which unfortunately the funders don't want us to do. We've missed out by, I think we were ranked third in a recent panel, and 2 were funded, or we were 4th and 3 were funded. But yeah, it's definitely something that is got potential to explore. But it costs development effort, and that development effort generally with research funding needs to be tied to a piece of research that's been undertaken and make a case for why that's important.
Yeah, Miriam.
So that was one of my questions, but I had another small question. You mentioned that you use the CUDA stream feature. Do you use the
Yes.
graph API as well, or just stream?
We do not use the graph API, and the reason that we do not use the graph API is because although our DAG is fixed, it's a fixed DAG, but there are parts of the DAG that may be on or off depending on the state of the system. So for example, if all agents are in one state, we don't want to simulate the whole graph, which means that as it stood at the time of the implementation, the graph API couldn't handle and couldn't deal with that. I think we've got an issue for this on the repo somewhere, but I think that may have changed now. So there's the potential that we could use the graph API, which would then hide the overhead of a lot of the kind of the kernel executions that take place. Yeah.
Thanks.
Arian?
So what I understand from your remark about that the go on to run the order of billions of agents is you're currently only running on a single GPU?
Yeah, again, another great question.
Yeah, so is there anything, like, are any issues that might complicate going multi-GPU, or is it more the case that there hasn't been a need for it before?
Loads of issues. And again, this was the topic of one of the funding things of the most recent funding thing that we put on was cross-platform and multi-GPU to support exascale simulations. There are challenges when it goes to multi-GPU. So And there's the same challenges that you get when parallelizing, namely that things communicate and things move, so they're dynamic. So you're the process of load balancing, and so first of all partitioning and then load balancing is a dynamic one. So you can partition the environment, but then as you saw with the murmuration of birds, things move around and you may end up with idle GPUs and full GPUs. So there is a historic version of Flame that was built for MPI before the GPU version. So there is some nice research that we can leverage there, some nice kind of implementation that we could leverage there should we have that opportunity. But it's not straightforward. Going to multi-GPU is not straightforward. The first thing that we would probably do to support very large models is use managed memory, which we don't currently use, which would mean if you had a 2 terabyte system memory, you could use a single GPU and it would page information in and out. That wouldn't necessarily be very efficient, but it would mean that you could run very large models at least. So that would be our first step. And I think that's something we have some funding to do some development starting the end of this month or the end of June. So that'll be one of the first things we implement. Multi-GPU is a much bigger task to undertake though.